So our next presentation will be Maria, and excuse me if I mispronounced, Guinazu, sort of, who is from the University of Chile, in Chile. The novel Deep Medicine and Cancer Prevention Through Early Detection. So let's join her, welcome her to our conference.
You? Yes, there.
I'm going to just swap your mic out with this one.
Yes.
Thanks.
Yeah.
There you go.
So, right. Well, thank you very much. So, before starting just my talk, I will give a little bit of introduction of certain concepts that we need to bring to try to reach exactly our product or our system that we create. So sorry, it's in Spanish, it's called Camellia, Cancer Melanoma Inteligencia Artificial, or Artificial Intelligence. And then I will introduce you, or I will present you and show you how did we made it, the whole system. So in this, I think that I will try to be very simple in the explanation, but I think that will be, I hope that it's been quite useful for all of you who use electronic health record, any platform, absolutely everything related with artificial intelligence. So first of all, I have been talking the whole day. Recently, not quite recently, at least the last 30 years, we have been producing a lot of data in the health system. So, it's growing increasingly a lot. And in research, we have been, apart from having data, a lot of data from different sources. So we have from electronic health records, all the omics, and we need to combine all this data in the right way, making the right question, to produce, for example, a drug specifically for the treatment, or a right treatment for the person. Not the right treatment for the right person, because we know that this is impossible. We work with groups of people, so the one that we go in research, we know that it's not one by one. And then, so if we put all this together and think about data, in all the different set of organizations, with everything that we are producing, we have data and data and data. That data we have to process, to compare, to then we produce predictive models, and then those predictive models then go to platforms, any platform that you're normally using every single day, or any application. So then, this is one thing from one side, data. The other thing is we have been reducing with the timing the experiment. For example, it has been presented not so far away. Google from DeepMind present this system which is called AlphaFold. That's something that took in the past 3 years now take 3 minutes. Yeah. So this is because to generate a 3D models, protein models, even go further, and they develop a possible protein that doesn't exist in the real life. So all the people that are working with different models will understand that this is really, really very important. First of all, if you're working, everything that happened with the vaccine and COVID, with all the predictive model, that helps a lot to develop vaccines. So now, I'm not going to enter in all the problems that artificial intelligence have, otherwise we will be talking the whole day, the whole afternoon at least. But we have a problem with mixed diagnostic, but not the artificial intelligence, if not us, we, the doctors. Why? Because sometimes we are tired. We have to manage a lot of data, and we just sometimes are producing, and making mistakes when we are making a diagnosis. So I will present you here with the imaging. This is a study that we have done with this kind of artificial intelligence system that is a convolutional network, that then I will explain you what is the meaning of that. But let's say from the moment that is using this artificial intelligence system, predict, and they found this nodal. They discovered this nodal they were able to diagnose using this predictive model, whereas when radiologists failed to diagnose, yeah? So it's not a criticism, it's really recognizing that we are humans and sometimes we just made mistakes, yeah? So it's not that artificial intelligence is coming to take over and everything. It's just only a good tool to help us. At the end of the day, we make the decisions. We scientists, we doctors are the ones who make the decisions. Thing is, the better that we produce a model, the better that we'll predict the model, and that will help us the best. So now if we go with cancer, so this is, I mean, I work a lot with tissue. For me, this is kind of wow. Just looking slides, just a slide of tissue. There are models that can predict mutations, tumor versus normal and origin of the tumors, or structural genomic changes, just only looking a picture. I don't know if you were in the morning, but one of the guys mentioned that doing in another system, they were just to be able to predict even genomics mutations and things like that. Well, this is in the way that we feed the system, that we create the algorithms, and we teach the algorithms to recognize the things. So at the end of the day, we are in the back of everything. This is other example that using the same thing, the radiology imaging, you can, a system can even guess the race or test or diagnose diabetes. So imagine that. Seeing this, we can just see or say that person have to, you know, the possibility to become diabetic. So that is a lot. So now, if we put together big data, personalized precision medicine, which is, I'm not going to enter, no, but is this kind of treatment for a group of people. And the imaging, this is the way, like, you know, our system of deep learning is the algorithm behind that, behind all that combination. So at the end of the day, and the product that are going to, the system that we create, and this is very important, we are mixing data from different sources. So at the end of the day, we need to change all those data to become in one language, because it's like then we are mixing Mandarin with English and Italian. It's not going to work. So I will explain you how we can do this in a very easy way. Well, hope so. It's not easy at all, but I hope that I explained to you in an easy way. So, but the point is, the more important point is we are mixing data from imaging and clinical data that we call metadata, which is language. And it's the famous natural language processing, ChatGPT, that I don't like it at all, but you know, it's that. So ChatGPT managed with that, natural language processing, combine words and this kind of thing. So just from the beginning, look, this is our problem, yeah? So we are going to combine two different things, yeah. So what is now the famous deep learning? Well, deep learning is an algorithm which is capable to learn when you give a task. And the thing is, the more the problem that resolve and the more data that you put, the better that is the come out, yes, of the prediction. So in this, how the things work, how is the system? What is called deep neural network? Because it's more or less sort of, I am a neurologist, as our brain works when we are thinking, sort of. So in this system, which is this network, we have different entrants, so different data, yeah? And each data, each point, then go from deeper in knowledge and become each point related with more 2 or 3 points like this. So better I put a draw. So let's think that if you have a car, if you take a little bit of the picture of a small area, yeah, then that small area have, let's say, 100 dots. Then you take this and you see a small area, and you see those dots more in details, and that dot more in detail. So each of that is the one that we call a hidden layer, more hidden layer. So if you think in this way, you are becoming, that is why the images they are better than us to predict. Because now I try to compare with the image. So imagine this is the image, the car, or this entrance. Then imagine that each of these points, yeah, then becomes so precise that then can check a group of these, show a tumor 1, the other, and be able to, you know, diagnose a tumor 2, which we are not capable to do that. That was the image, and sometimes the predictive model, the convolutional network, that is the one that I am using, are so precise. Yeah, it's because we are, And this is that it's a black box. As you realize, no, we can drive a little bit, creating different kind of algorithms inside to, I never say that to be 100% precise, but with a certain of precision to get the diagnosis. And the important thing, and this is why we use this convolutional network that from now on onwards I will call CNN, is because with both we can use for imaging and for natural language processing that are the two that we need to create our model. So before I enter to the model, it's a quick kind of summary how deep learning is helping in oncology to go further. You have been presenting several things, and if all of you use models, it's a thing that have been, thanks to artificial intelligence, that are being improved. So the outcome of precision medicine to predict tumors, to assess treatment, to enable personalized treatment, to plan to improve the health of the patient. The image recognition that I already explained to you, that is really very important. We can do all this screen, reduce the timing of working, and get a better outcome. Then this automatic decision, okay. Sometimes, and it's one of the things that our system does too, sometimes when the patient goes to the hospital, they get diagnosed and everything, spend, I don't know, in the system in Latin America is years. I don't know here how it is, but sometimes you go to the doctor, you go to exams, and then you get the diagnosis 8 months later, and if you are sick, wow, 6 or 8 months later are quite a lot. So with these tools, used in the right way, we can just reduce the time of diagnosis, and our tool diagnose automatically. So finally, I will say that this was our question. So it is possible, for this, using the CNS and combining imaging and natural language processing for us to create a tool to diagnose melanoma. Well, actually, we diagnosed 9 different lesions in skin lesion, but let's talk about melanoma, that's the important one. So what was our opportunity? Our opportunity was trying to find a monitoring tool. So try to, sometimes if you see in your skin appear something very little, that is nothing, you don't need to be worried about it. But as soon the time comes, could be getting, being a melanoma. So if you don't follow, if you don't do the monitoring, then suddenly, so the disease doesn't appear in 20 hours, in 24 hours, but yes, after 6, 8, 11 months, 2 years time. So with this kind of system, you yourself can do the checking. So this is being not just only the whole system being centered in the person, in the patient, if not with the power to the patient. Yeah. So this is the thing that we call in England smart patient. Yeah. So it's participating all the time. This is just only the problem that we have from melanomas, yes, from they represent the 4 or 6% of the skin cancer, and then 72% of the death. In Chile, in spite of being, a lot of things have been done, still there is an annual increase of melanoma from the 3 to 7%. The problem in Chile, which happened in a lot of countries when a lot of people live outside, work in the field, are completely exposed to, to the sun. So this is not just only a disease that affects, if not, it's a very social problem too, because it affects a lot to more low income people. So it's not, it's even worse for us in that way. So, the idea is this word, which is lovely, which is prevention. Yeah. So we developed this system. And it's a system, as I said, that can analyze simultaneously a lot of images. It's easy to be used because the thing that we did is, and now I will show you what is the main step, is the only way to be able to be diagnosed is you go to the dermatologist who have a dermatoscopy, who will take a picture and can just, tell you, okay, you have this and that. But we did a further step, and we teach a system to using just only your camera, your cell phone, take a picture, and then diagnose by yourself this kind of disease. So soon, we have been fighting against Google for 2 years. It's going to be put in the Google system, so everybody is going to be able to use for free. So I am extremely proud and happy about that. It was a huge fight. So, and I'm not going to enter in all the challenges that we're facing, the people that work in artificial intelligence, because I am, again, but the system have to be rigorous, validated all the time, and the algorithm had to be tested all the time. So this is not just only for my thing that I'm going to present to you. If you are going to use anything in the future, when somebody is coming to offer to you any platform and anything, please be very upset about this, obsessed. They say, how many times do you do the checkup in this and that, the process, because otherwise the algorithm is not going to work. So it's going to be lovely and beautiful in the engineering point of view, but extremely bad in the medical point of view. So anyway, melanoma. Melanoma is when melanoma happens, yes, it's just very short. When the melanocyte produce melanin, yeah, but starting just, growing uncontrollable, like any cancer. I'm not going to enter in that, more than me in this. And more of the skin cancer happen here in the epidermis and in the three, the three group of cells, squamous, basal cells, and melanocytes. So this is important, yeah, to have. We are not having just only one type of cancer. And then this is extremely important too, that the melanoma is a more aggressive cancer, skin cancer. So how we are starting just to try to, when we create the system. Luckily us, the dermatologists, use something very simple to try to, when they are looking pictures and try to see, okay, this is a regular and normal one, and this is something that is already or will become a bad cell. So in here, you have something that this is benignus and this is malignus, yeah? So first of all is the asymmetry. So when it's benignus, it's completely symmetric. When it's malignus, it's completely asymmetric. Secondly, the borders. You see, this is irregular, the border. So when it's not, it's regular, perfect, be happy that you have no problem at all. When you start seeing in your skin this kind of thing, be worried. Then the color, in general, is homogenic when it's benign, but when it's malign, you have a kind of starting just changing the color and become darker, certain areas in the same spot. And then the diameter, so when everything is homogeneous, the diameter is perfect and doesn't have kind of different size of like here. And this is just to show you the evolution of something. This is the evolution of melanoma. So something that could happen, could appear at the beginning, something, oh no, don't worry. But later on, you have a melanoma. As I say, it doesn't appear like suddenly. It's something that appears with the timing. So this is how a dermatologist work. So they have the cell phone, and this is the dermatoscopy. So they put, here you have the skin, here you have the dermatoscope, yeah, and you have here the cell phone. So the dermatoscope amplifies 10 times the image. So you take the pictures, and this is it. This is how the dermatologist work, and then the dermatologist, stores the image. So how did we develop the system? So, I will show you, I will talk a little bit about how we develop the predictor model, the application, the testing, and then the standardization, which is the more important thing, because we pass from using the dermatology, the dermatoscopy, to use exactly just only the camera from our cell phone. That took a lot of work in working with cell image, a lot, plenty. Okay, so how did we do it? So we didn't have a source of pictures so big, so we took from the whole Europe. There is an open source, so we took 140,000 pictures from 2017 to 22, yeah? And we consider 9 lesions from the skin, and 14 architectures. These architectures, do you remember the CNNs? Well, each of one of these were 14 of these convolutional, 14 different models, and we combine with different size of the pictures, so we have 84 combination. That is, if you work, I don't know how many people work with DNA and cloning or things like that, but it's like you have a whole DNA, and then we start taking each, set of cysteine, so CCTT, so it's exactly the same. We work in that way, mental. So this is how one is divided in pigment cells and non-pigment cells, and those are the nine less classifications. So in general, this is how we started from the beginning to control. You always, when you work, when you are designing something, you have to have something for training and something for validation. So people who work in, you do research, you know that you always have to have your control. So all the time we call this validation. So something that we do it and we validate it with a new source of data and we prove it. And then we move a little further and then again further and like this. So those are all the combination of size, as I say, 6 different sizes. Because the other problem that we face is dermatologists have no protocol to take pictures. So they take pictures in different sizes. So then how can you compare different sizes of a picture? And if I want to use the CNNs, do you remember that the dots and blah, 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 the layers, but to be able to compare layers have to be taking all of them in the same way. Otherwise, I'm going to be making a huge mistake. So we have to standardize all that too, who took us quite a lot. So, and then the predictions, so the algorithms, as everything in life, have different metrics that we can use to say, okay, this is a good one and this is a bad one. The important for us in medicine is the recall. Recall, what does it mean? Recall means it's going to be giving us the positive from the thing that we are diagnosing, and I will show you now. So this is, those are the CNS. Remember that we use a lot of them. Each of them is this convolutional network, one of them, each. Those are the size of the different picture size. And recall, if I say, for example, 088, what does it mean? That from 100 pictures that I am diagnosed, that my system is diagnosed, 88 are correct. So I have the certainty of 100 patients that I'm seeing and I diagnose with, they have cancer, melanoma, no melanoma, nevus, or whatever. The system that we develop, the 88, we are certain that we are right, at least. So this is really very good performance of our systems. But apart from that, we run all of them with all the size and we choose the best one, so our winners. So at the end of the day, this is a lot of work I'm not going to show you, but the important one is we choose those, we made the prediction, and how did we make it? We made it in a comparison as a percentage, yeah? So at the end of the day, our system was able to, this is a melanoma, so this is a percentage of the other lesions, the 9, and you see the melanoma. Yes, so they said that 90% of the possibility that this is a melanoma, and it was a melanoma. So this is how our system works so perfectly. Then we developed the app, very short. The app, everything that you see in your platform, everything that you face is called front end, is the one that you see in front of you. And this, you have to have a code that we need to create. Which time that you go from a place and you display the part, and then when you are open anything in platform and you are writing the patient data and scroll up and down and all this kind of thing. Well, this is because we generate a system that teach the staff to the front end to work. And in the thing that we call backend is where you put all the stuff that in Python, that is the system we use in medicine, to create all the algorithm, all the data, the database, all the things that we say, now you go from here to there, compare this and that, and how do we read the image? That is now the more important point. So do you remember that I said the image is image, and then we have metadata, so this is text and this is image. So then we convert both of them and become just only one language in Python. So this is why we imagine, even now sound is a wave. So the way we translate in numbers become the same like a metadata, an image. That is why we can compare in predictors sound, image, and text. And at the end of the day, we can do anything. As soon we try to find that all of them translated and become just only one language. Yeah. So very fast. Then we test the application because if you remember, we have with people from Europe, and we have the 6 skin. So there are 6 types of skin. So we have all the representation of the skin, but we need to do in Chile. So we give to 50 dermatologists who took the picture, use our system, and then we refeed it with these novel new pictures from Chilean, and then we retrain all those CNS again, and then become our predictor more closer to predict diseases from Chile rather than whole Europe. But we're very lucky because now we have European and Chile, which is more or less Latin America, so, you know. And then we standardize the system. Oh, this doesn't, sorry, move a little bit. But standardize the system to be able to pass from taking the picture using the dermatoscopy, yeah, to use just only the camera. So that took quite a lot. Sorry, you need to trust me that we did in the right way. But we took 140 dermatologists. We may work with the poor dermatologists in Chile. Each time they arrive to a place, oh my God, no, Flavia again. So, but you know, they help us a lot in that way, using our system. So we teach the people where to, you need to check in the system, you know, that when you are taking the pictures, it's the first step. You need to teach the people are going to use the application as soon as you open the application. And then, how many minutes do I have? Oh, okay, well, as the thing is, this was a movie. I want to show you how the system works, but yeah, it's just, sorry.